look at an integration technique called improper integrals. And to evaluate an improper integral, we must first recognize that there are two types to consider. The first one is where I'm looking for the area of the curve and I have this infinite interval of integration over here. It goes on forever. It never ends out here. And then the other one is when I have an unbounded integrand within the interval of integration. So in other words, we have a vertical asymptote and just keeps on going upwards and upwards forever and ever and ever. So we have these two situations. So we're going to take a look at how to deal with these things, and I'll give you the steps and then we'll go ahead and get busy with some examples of different types. Right? So to evaluate, we need to do a couple things. We're going to replace the infinite part. So in this case we have inside here, and this one's up here in the limits. The infinite part of the integral with a variable and an associated limit. And you'll see what that looks like here in a minute. We're going to integrate and compute the limit of the result. If the limit exists and is finite, then the integral is said to converge to that value. And if it doesn't exist, then the interval is said to diverge. So let me go ahead and that's pretty much it. And we're going to show you how to work this out by examples over here. So let's take a look at our first example. So we're going to look at the integration from 1 to infinity of 1 over x dx, or excuse me, 1 over the square root of x dx. Here is a visual of it. See how it continues on forever in an infinite fashion. So the first step was to replace the infinite part with a variable and an associated limit. So it looks like this. We're going to take this right here and write it as the limit. And usually what we do is, for me, what I do is I use the b if I have an upper limit that's infinity. So we're going to use the letter b. The limit as b goes to infinity of this, from 1 to b. So that's how we deal with these limits of integration up here in this fashion. Other than that, everything else is exactly the same. This is x to the 1/2, which will bring up as x to the negative 1/2 dx. And so this is the equivalent, and that's how we would deal with that situation. Once I do that, I just take the integration of this quantity right here, and then after we do that, we'll do the limit of whatever that result is. So this is going to be the limit. Make sure you continue to write this out until we actually take the limit. And then we want to integrate this, so we're going to raise the power 1, divide by the raised exponent. So we're going to go up to positive 1/2 and divide by 1/2, which makes it equal to 2x to the 1/2. Evaluated from 1 to b. Okay, so now we're going to do the upper limit minus the lower limit for this part right here. We still have the limit as b goes to infinity. And we're going to have 2b to the 1/2 minus 1 to the 1/2. Okay? And so as I do this, as b goes to infinity, this quantity right here, because it's the square root of b, is just going to keep getting larger and larger and larger, which means that this limit goes to infinity, does not exist, and so this limit diverges. That's how that works. Let's take a look at another one down here. Same type, this time I have an x squared on the bottom. We do the same exact process. The infinity is on top up here, so I'm going to do the limit as b goes to infinity. You can use any letter you want. I just like to be consistent, and you use the letter b up top. Bring this to the top as x to the negative 2 dx. And then we want to take the integration of this. So this is going to be the limit as b goes to infinity of what? Raise the power 1, divided by the raised exponent, evaluated from 1 to b. Okay? This is the limit as b goes to infinity of what? Now this is going to go to the bottom, so it's going to be a negative 1 over x, and so this is going to be a negative 1 over b minus a negative 1 over 1. So you can see this is going to be plus 1 right here. As b goes to infinity, this quantity right here will go to 0. And this will be plus 1, so this is 1. This converges. and then it's also this value. So this thing right here equals 1 is what it means. Okay. Here's another example. This time you'll notice that there's no infinity in here, but I have an unbounded integrand in here. So this is going to keep on going up here and forever. So how do I deal with that one? Well, this part right here never reaches it, so it's kind of like undefined here. We need to stay within our interval here, excuse me. So between 0 and 1. So when I do that, I'm going to replace this 0 with a value. And when I replace the lower limit, I use the letter A. So this is the limit as A approaches. Now what am I approaching? I have to stay within this interval, so I have to approach 0 from the positive side. So that's how that works. We need to stay within the interval, so we need to go from the positive side to stay within this interval. And then from A to 1. So that's how you would set that one up. Here's my limit. And then this quantity here is going to be 3 over 2 x to the 3 halves. I do not think that's x to the 3 halves, excuse me. To the 2/3. There we go. And we're going to go from A to 1. Yep, raise to the power 1 gives me 2/3. Divide by 2/3, flips it over, gives me this quantity right here. All right? And so then we have what? Upper minus the lower. Three over 2, 1 to the 2/3. 3 over 2, A to the 2/3. Okay? So as A goes to 0, this quantity here will be going to 0, and this quantity right here becomes 3 over 2. And so this one converges. Okay? So what I stated over here is, why is it 0 to the plus? Because we need to stay, nope, you can't see it, excuse me. We need to stay within the interval of integration. Okay, so if you have something like that, again, that's how you're going to do it, with a little plus or a minus, depending on which side the interval of integration is. I mentioned over here that at the lower limit, x equals 0, the function is undefined. Just want to clarify that kind of stuff for you. At 0, you're undefined. So I can't take a limit from 0 to 1, it's undefined at 0. That's what triggers this process here. Okay? Let's look at another example that I have over here. Just a bunch of examples left, but there's little key things on each one of these that we want to look at. Okay? So see if you can do this one. We're going to go from negative infinity to 0. Take a moment here, pause this video, see if you can work this one out by yourself, and then I'll come back and I'll show you the solution that I have. And go ahead. Okay, so we're back. Hopefully you got an answer. Let's see how you did. The limit, the infinity is on the bottom, so I'm going to start there. I'm going to call that A, so this is equal to the limit as A approaches negative infinity. And this will be from A to 0 of this quantity. And hopefully you recognize this right here as one of our special integrations. 2 is a constant, so that just comes out in front. This is going to be the arc tangent. So this is the limit as A approaches negative infinity of 2, the arc tangent or inverse tangent of x, evaluated from A to 0. And so then we plug everything in. So the upper minus the lower, arctangent of A. Okay. The arctangent at 0 is 0, so this is going to be 0. And then the limit as A goes to negative infinity, so this quantity right here is going to negative infinity. So if you remember what this looks like, arctangent is bounded below by the value negative pi over 2. So as A goes to negative infinity, okay, remember the arctangent looks like this. It has an upper horizontal and a lower horizontal, and it kind of does something like that. So it's getting closer to this one as I go to negative infinity. So this is going to be minus the 2, and this is going to go to negative pi over 2 like so, which means this is going to go to pi, and it converges. Okay, so hopefully you had that. If you didn't, let's try with this one right here. Take a moment, pause, and see if you can solve this one. Okay, so hopefully you got an answer. Here's my infinity up here, so I'm going to use the letter b. This is equal to the limit as b goes to infinity, the natural log of 5 to b, e to the negative x dx. So as I take the integration, I'm going to get a negative e to the negative x, evaluated from the natural log of 5 to b. Very important that you don't skip these little limits, so you got to make sure you write them every single time, just like I'm doing here. Plug in b, plug in the natural log of 5. The limit as b goes to infinity. So let's clean this up just a bit. That's a negative, so it's going to become a negative 1 over e to the b. This is going to be a plus 1 over e to the natural log of 5. As this goes to infinity, this quantity will be going to 0. As b goes to infinity, this has no b, this is just simply going to become e to the natural log of 5, just becomes a 5 here, so this is going to be plus 1/5. So this is 1/5. And so it converges. Okay, so I hope you got that answer. We got some more here. This one's a little bit more tricky, so we're going to walk you through this one right here. So, why is this here? Okay, and the reason why this one is here, and it's an improper, is because this is improper because the natural log of x is not defined for the lower limit. 0. The natural log of 0 is undefined. Okay, so we need to take this and we're going to do the limit as a approaches 0 from the plus side, and we get the natural log of x dx. So how do I integrate this? Well, from our past problem, integration by parts, we got to do integration by parts here, where this quantity right here is my u, and my dv is dx. So my du is 1 over x dx, and my v is simply x. Okay, so then the limit as a goes to 0 plus of this quantity right here is going to be u times v minus the integration of v du, so that times that is 1, this is just simply going to be a dx. And this is still going from a to 1. This one is evaluated from a to 1. And then we clean this up and we integrate that quick piece right here. And so now I have x, the natural log of x, minus x, and that's evaluated from a to 1. So this is going to be the upper minus the lower as a goes to 0 plus the natural log of 0. The natural log of 1 is 0, so this part is 0. We have a minus 1 here. Okay, over here we're going to have a minus a natural log of a, and then we'll have a plus a. So as a goes to 0, okay, well, let's break this up. As this one, these are all pretty simple, but this one is a little bit tricky. We got to look at this one right here, because let's take a look at it. Let's break this apart. So this is a goes to 0 plus of negative 1. I'm using the properties of logs that allows me to do each one individually. This will be a natural log of a, and then plus the limit as a goes to 0 plus of a. Okay, so these are pretty straightforward. This one is a little bit tricky because this is the indeterminate form. Okay, if I put in 0, I'm going to get 0 times infinity. Okay, and that's not going to work for us. Or negative infinity, excuse me. So we have to go and use L'Hopital's rule and stuff like that. So this right here is the indeterminate form. So what is the limit as a goes to 0 plus of this? We need to rewrite it as the natural log of a over 1 over a. And now I have infinity over infinity, okay, which is the indeterminate form, which means I can take the derivative of it. Goes to 0 plus, this is going to be 1 over a, this will be a negative 1 over a squared, which is the limit as a goes to 0 plus. Clean this up, gives me simply negative a. So this will be 0. So this quantity right here is negative 1. This will be minus 0. This will be plus 0. Negative 1 is our final answer here, and so we know that this is going to converge. Okay, so I'm going to show you my notes for this one so you can see it a little bit better. That's what I wrote out. So take a moment here and you can see that the wording down there below. Okay, and just add that to your notes. Okay, so let's take a moment here. We got a couple more examples to go, using other techniques for help us solving this problem out. So here's this one, okay? And again, we have a couple things going on here, so be careful. Just because you see the infinity up here doesn't mean it's only that one, because notice also that it is undefined at 5. So we got a problem with the upper and the lower, okay? So how do I go about doing something like that? Well, I need to split this interval up, and you can pick any number to split it at that you want, okay? And so, in other words, I can write this problem right here as the integration from 5 to 6 of this. And again, you can pick any number, that doesn't matter, and this one's going to go from 6 to infinity. So if you don't like 6, you can pick a different number, but it doesn't matter which one you pick. Okay? Now, for this to converge, both of these must converge. Okay? So they have to both converge to have a convergent answer. So let's see what we get here. This one has the problem on the bottom, so this is going to be the limit as a approaches 5 from the positive side, from a to 6, 1 over x minus 5 dx. And this one's going to be at the top, so this is going to be the limit as b goes to infinity of 6 to b 1 over x minus 5 dx. So that's how I would set this one up. Okay? So this is the limit, and I'm going to go a little bit faster in writing this stuff out for the sake of the time on the video. You can go and make sure that you understand all the steps that are involved here. As b goes to infinity, the natural log of x minus 5 from 6 to b. This is a. So the upper, this will be 1. The lower, a minus 5. The limit is b, goes to infinity. The upper, and then minus the lower. All right, so the ones here, natural log of 1, natural log of 1, these will go to 0, okay? And this right here, as we get closer and closer, this right here is going to go to negative infinity. This one went to 0. This one's going to go to infinity. This one's going to go to 0. So we can see clearly that this right here, okay, is going to be divergent. Okay? And the last one over here, you can't do u substitution because you don't have the u. But so the other techniques that we can use here is partial fractions. This was a technique we learned in the other day also, in the other video. So we take this quantity right here, and we factor the bottom, and then we set these up over separated fractions, like so. And then plus bx, and then at x equals 2, I get a 2 minus 2, and so we know 2b, so 2b equals 8, and so b equals 4. And then at x equals 0, I get 8 equals a 0 minus 2, b times 0, so that's gone. I get negative 2a equals 8, and so a equals negative 4. So that allows me then to take this quantity over here and write it like this. This is the limit as b goes to infinity of 3 to b, and then this right here I can write as 4 over x minus 2 minus 4 over x dx, which allows me then to integrate this, and I will get 4 the natural log of x minus 2 minus 4 the natural log of x, evaluate from 3 to b. Okay, and so as we continue on, you can do this a couple different ways. One thing here, you can simplify this out by combining it into one log if you wanted to. You can do it like we did the other one and separate it out. In the notes I wrote it as I combine them so you can kind of see how you can use that to help you out. You can factor out the 4 first, and you're left with just the 2 logs that are subtracted, which means this one will go to the bottom of a fraction. So I can write this using my condensing rules for logs as 4 times the natural log of x minus 2 over x. And that kind of simplifies our work just a bit, so I don't have a big long string. If you recognize to do something like that, you can go ahead and try it. If you don't, you can just did it like we did the one above, like this right here, totally fine. I just wanted to show you that. And so upper minus the lower, we got b minus 2 over b, and then 4, 3 minus 2 over 3. So what is this going to be? As b goes to infinity, this right here is irrational. This right here is going to turn into a 1. So this becomes 4 the natural log of 1 minus 4 the natural log of 1/3. That's 0, okay? And you end up with simply 4 the natural log of 3. If you're not sure about the signs, then let's look at it from this point of view. Well, just factor out the -4. Okay? And then everything comes out in the end. Well, there it is. You can go work on that and see if you can figure it out. The reason it turns positive is because you split this apart using exponent log rules as the natural log of 1 minus the natural log of 3. That's where you get the double negative. So look at it, make sure you can do that little mathematics stuff from when we talked about expansions of logs. If you have any questions, let me know about that part of it right there. And that is the end of this video. So I hope that helps you in performing those kind of integrations.